Assalamu alaikum. This is chemistry 12th, and our today's topic is the properties of these alkyl halides. So, dear students, as we have already discussed the synthesis of these alkyl halides, halides. Now, as far as the properties of these alkyl halides are concerned, we have got two types of properties. One that is the physical property, and the other is the chemical property. Now, as far as the physical properties of these alkyl halides are concerned, we have got first of all we have the physical state. Now, as far as the physical state of these alkyl halides is concerned, the lower members of this family, this homologous series, they are colorless gases. Now the higher members of this family, they are liquids, whereas those which have got high molecular masses or they are solids. Now this is the physical state of these alkyl halides. Then as far as the solubility is concerned, as far as the solubility of these alkyl halides is concerned, these are insoluble in water. This is due to the lack of hydrogen bonding in these alkyl halides. However, these alkyl halides, they are readily soluble in case of organic solvents, like we have got ether, we have got acetone, we have got this benzene, etc. So they are readily soluble in organic solvents, being organic in nature. Now as far as the density of these alkyl halides is concerned, or density, as you know, that it is the mass over volume. Now since these alkyl chlorides, they are generally lighter than water, so their density is less as compared to that of water, whereas the corresponding alkyl bromides and alkyl iodides, they are heavier than water. Obviously their density will be greater. Now as far as the boiling point, this another physical property which we have, that is this boiling points. And now boiling points, as far as boiling points are concerned, the boiling points of these alkyl halides, they are generally higher than the corresponding alkanes. Now this is because of their polarity and strong dipole interactions. Now because of this dipole interactions, and because of their polarity, the boiling points are, they are higher than the corresponding these alkanes. Now because of this polarity, this leads to strong dipole interaction between these haloalkane molecules. Now the boiling points of these haloalkanes, they decrease in the following order. See here, the alkyl iodides, they have got higher than alkyl bromides. Then you have got they have which in turn are greater than alkyl chlorides, and then alkyl fluorides. Now the reason behind this is that with the increase in the size of halogen atom, here iodine, you have got bromine, here you have got chloride and fluoride, and now since the size of this halogen atom, size and the mass of the halogen atom increases, the magnitude of the van der Waals forces of attraction also increases. And also we see that the boiling points of the straight chain molecules or straight chain compounds, they are greater, or they are higher than the isomeric branched isomeric these branched chain branched chain compounds or branched chain molecules. Now again, this is related to their surface area. Since in a straight chain molecules, the surface area is greater, since boiling points are directly related to the surface area. So obviously the boiling points of these straight chain molecules are higher than those of isomeric branched chain molecules. Now as far as the chemical properties are concerned, these alkyl, these were the physical properties. Now as far as the chemical properties of these alkyl halides are concerned, chemically they are extremely reactive in nature. Now as far as the reactions of these alkyl halides are concerned, we have got various types of these chemical reactions. We have got nucleophilic substitution reaction, we have got elimination reaction, which is also known as dehydrohalogenation. Then we have got reaction with metals. Then we have got reduction. Now as if we look at this CX bond. Now CX, since X is the halogen atom, it can be chlorine, it can be bromine, it can be iodine. Now this CX bond, it is because this of the strong this electronegativity of this halogen atom, the shared electron pair is displaced slightly towards the halogen atom. As a result of this, the bond gets polarized, with carbon acquiring a slight this positive charge, while as this halogen atom, it develops a slight negative charge. Now as a result of this carbon, because of this because as the since the bond gets polarized, this carbon becoming positively charged, while as hydrogen, this halogen atom, it develops a slight negative charge. So these are easily attacked by the nucleophiles. Now this carbon atom is easily, this carbonium, now ion, this ion, it is attacked by the nucleophiles. And what are these nucleophiles? Actually these nucleophiles, they are the negatively charged species or negatively charged agents. We have got hydroxyl ion here, we have got cyanide, we have got this RO minus. Now since these are negatively charged, so they behave as nucleophiles. Now we may have the neutral molecules, like water molecule, we have got this ammonia. Now these neutral molecules, they may have got an atom with one or more lone pairs of electrons. So these nucleophiles are electron rich species, and they are nucleus, these we can call them as nucleus living species, since they attack the electron deficient sites. Now in this case, in this CX bond, we see that CS has got a partial this C has got a partial this positive charge. So this is an electron deficient site. So obviously the nucleophile will attack this carbon atom. Now as a result of this, the incoming nucleophile, it should be stronger than this halogen atoms. So this halogen atom being a weak nucleophile, it is easily displaced by a strong incoming this nucleophile. Now these, as far as these nucleophilic substitution reactions are concerned, we have got various types of these nucleophilic substitution reactions. For example, we have got this we have got the substitution by hydroxyl group. Now these alkyl halides, when they are treated with aqueous potassium hydroxide or moist this silver oxide, they give rise to the formation of these alcohols. Now you see here that this is alkyl halide. When it is treated with this aqueous potassium hydroxide, this halogen atom gets replaced by the hydroxyl group, and we get the alcohol. And this potassium, it combines with this halogen atom to form this KX, or that is called this potassium halide. Now here I will show you this is ethyl bromide. When it is treated with aqueous potassium hydroxide, we get ethanol and we get potassium bromide. Now if we use this moist silver oxide, now this moist silver oxide, when it is treated this moist silver oxide, when it is treated with water, it gives silver hydroxide. It forms silver hydroxide. Now this silver hydroxide then reacts with this alkyl halide molecule to form the alcohol plus silver halide. See here, this is RX, it is silver hydroxide, we get AgX, and this X gets replaced by hydroxyl group, and we get the alcohol. So this is how how the substitution of this halogen atom takes place by the hydroxyl group. That is when they are treated with these aqueous aqueous alkalis like potassium hydroxide. We have got aqueous sodium hydroxide. Now then we have got the substitution by alkoxy group. Now in this reaction, what we do, these alkyl halide molecules, they are treated with sodium alkoxide or potassium alkoxide to form the ethers. This is a well-known reaction which is known as Williamson's reaction. This is very important reaction for the synthesis of these ethers. So in this reaction, an alkyl halide is treated with sodium haloxide or potassium haloxide to give rise to the formation of ethers. See here, we have got here ethyl bromide. This, when treated with this sodium ethoxide, we get this sodium bromide plus we get diethyl ether. Now if we can use we can use these instead of this ethyl bromide, we can use methyl bromide. Then we will get then we will get a mixed ether, that is methyl ether. This is a asymmetrical ether. That means we have got two, the oxygen atom has got two similar groups, two ethyl groups, so this is diethyl ether. Then this is Williamson's reaction. Then the other reaction which we have got, that is this substitution by cyanide group, now, or cyano group. So in this reaction, what we do, these alkyl halides, they are treated with alcoholic potassium hydroxide, this alcoholic potassium cyanide. Now in this case, this halogen atom, it is replaced by cyanide, this cyanide group. So alkyl halides, when they are treated with this potassium cyanide, alcoholic solution of potassium cyanide, they give rise to the formation of these nitriles. This is here, this is alkyl cyanide, or we simply call it as nitrile. Now here we see this is a methyl chloride. When it is treated with potassium cyanide, alcoholic solution of this potassium cyanide, we get this is and this is ethane nitrile, or we call it methane. This is called ethane nitrile, or it is called as methyl cyanide plus potassium chloride. So this is how substitution of halogen atom takes place by this cyanide group. Since cyanide being a stronger electrophile than the halogen atom, it easily displaces this halogen atom from its compound, that is from a halide molecule, and it gets itself substituted, so we get nitriles. So then we have got a substitution by nitro group. Now in case of in this reaction, this is another type of this nucleophilic substitution reaction. Then in this case, we see that alkyl halides, when they are treated with silver nitride, they give rise to the formation of nitroalkanes. Now this reaction is used for the synthesis of these nitroalkanes. Now in this case, we see this ethyl chloride, when it is treated with with silver nitride, nitroalkanes are formed. Then another reaction, that is by isocyanide group. In this reaction, we see that alkyl halides, when they are treated with silver cyanide, they give rise to the formation of these alkyl isocyanides. This is the major product obtained, although there is the formation of this alkyl cyanide as well, but the major product in this reaction is alkyl isocyanide. Now this reaction is used, this is the best reaction which is used for the synthesis of these isocyanides, or we also call them as isonitriles. Now here you see methyl iodide, when it is treated with silver cyanide on strong heating, or heating it at a high temperature, we get this is methyl carbyl amine, or methyl isocyanide plus silver iodide. Similarly, we have got ethyl chloride, when it is treated with silver cyanide, we get this is ethyl carbyl amine, or ethyl isocyanide plus silver chloride. So there are there are a number of more reactions. Now today, then we will discuss those reactions in our next lecture. This is for today. Thank you very much.